Welcome back, guys. This little section of our packet talks about enthalpy, which is just like heat, but it's got another variable in it. Okay, so how are heat, which we use the symbol Q, and enthalpy, which we use the symbol delta H, referring to a change in heat energy over the course of a reaction, how are they related? Okay, well, your enthalpy of a reaction, which is your heat of a reaction, is equal to the heat, whether that's positive or negative Q, all over moles. So something really important that we want to point out is that enthalpy depends on amount. Okay, so depends on amount. Okay, and we did have a number 3 right over there, and we sort of ran out of space about it. So I'll just tell you a little other thing about enthalpy. It's something called a state function. And a state function is something that is independent of path. So, for example, let's say two students were synthesizing the same product, and they each took a different pathway. Well, ultimately, the heat change over that course of the reaction, as long as they both started out with the same reactants and ended up with the same products, if one student did it in 2 steps and the other student did it in 10 steps, they should still have the same overall heat change. But the 2 things we're going to focus on is, again, exactly what enthalpy is and how it depends on amount. So looking at this problem, they gave us a nice balanced combustion equation, which we've seen before. And then we also talked about combustion producing a lot of heat, right? That's what we do. We need that heat energy to keep us warm. We need that heat energy to fuel our cars, right? So that negative value of heat, that's a really good thing. We like those negative numbers here. So notice they said the heat of the reaction is simply negative 2,217 kilojoules. And some people go, well, where's the moles? Well, you can put this over moles of anything in the equation. We could put our kilojoules of heat over 1 mole of CH4. We could put our kilojoules of heat over 2 moles of oxygen. We could put our kilojoules of heat over 1 mole of CO2, and we can also put our kilojoules of heat over 2 moles of water. Okay, so let's read the problem and then we'll decide which one we're going to do. It says, what mass of natural gas, the CH4, must you burn to emit 267 kilojoules of heat? Notice the word emit. Emit means to release. So we want to know how much CH4, our fuel, do we need to burn just so we get a little bit of energy. That 267 kilojoules of heat to be released. So we're starting with a negative number. That's important that we read those words. We're not just scanning problems looking for numbers to plug and chug. So this is how much heat we want, and we want to know how much methane is going to be needed to be burned in order to do that. Well, now we're going to use our balanced equation. Okay, so our balanced equation says, well, if you have 1 mole of natural gas, you get negative 2,217 kilojoules. So we're going to use that conversion factor, that relationship that we were given in order to solve this problem. So since we want our kilojoules to go away, I'm going to put that value down here. So that way those units cancel because we're solving for the mass, which is related to amount. And then our balanced equation says we have 1 mole of methane. So if you notice, our kilojoules goes away, and we're left with our moles of methane. Then we always reread the question, what mass? So we don't have mass yet. So who remembers what variable we need in order to go from moles to grams? And I bet you know it, right? It's molar mass. So we would need to get the molar mass of CH4, the methane natural gas from the periodic table. So it's approximately 16 grams per mole. Okay. You, of course, have your little periodic table. You can get the exact molar mass. So 1 carbon and 4 hydrogens. And remember, molar mass is always over 1 mole of that substance. So now our moles cancel. And then we're going to get our mass in grams. Okay, so I want you to get this value. Okay, so you're going to figure out that value. What is our mass in grams? Okay, so we're going to work on one other little section in this video. We mentioned in previous problems they kept using the word calorimeter. Well, calorimeter is just a fancy word for a device that's used to measure temperature changes in reactions. So it's a device used to measure temperature changes. Remember, heat flows only when there is a temperature change. Now, there can be fancy bomb calorimeters that we use in the lab, and there's a picture on the next page. I talked about making a homemade calorimeter at home out of insulating styrofoam cups and a lid, and putting a thermometer into that. So our second equation that we're going to have, we've been using the MCAT equation in the previous problems. There is another way to find the heat of a reaction when you have a slightly different variable. So it says the heat absorbed or released by a calorimeter can be found with this equation. Q is equal to big C times delta T. Now this is different than our MCAT equation with little c, which is specific heat capacity. This is heat capacity of a calorimeter, and its units don't have mass in them. The units of heat capacity are typically joules over degrees Celsius or kilojoules over degrees Celsius. You could have calories over degrees Celsius, any sort of unit for heat, right? Even big calories, dietetic calories over degrees Celsius. Okay, so slightly different equation, and people go, well, how do you know which one to use? The CAT equation or the MCAT equation? Well, you use the one depending on, did they give you heat capacity in the problem, or did they give you specific heat capacity? So I want you to think about on your own these questions here that we talked about last week. Okay, so if the water in a calorimeter warms up, what type of reaction occurred inside the reaction chamber? So let's take a peek over here. Okay, this is a fancy bomb calorimeter. I'm not sure if you got the opportunity to use it in lab before we were shut down, but you could look at some neat videos online. Anyways, this whole insulated device is filled up with water, and inside here we have a little reaction chamber where typically we do, combustion reactions, burn something, and then you could do any sort of reaction in here. So the question is, right? If we had an exothermic reaction happening in here, what does exothermic mean? That means to release heat. Well, where does that heat go? That heat goes out into the water. So we would see our thermometer rise because the water is warming up. Okay? So back to our little question here. If the water in a calorimeter warms up, well, what type of reaction occurred? That was an exothermic reaction. Heat was released. Okay? And then vice versa. If the water in a calorimeter cools down, well, what happens? So if this water is getting colder, that means it's losing heat. Well, where is that heat going? The heat is going into the reaction. So the reaction is needing heat to break bonds and proceed to make new products. Okay, so that means those chemicals in there are absorbing the heat, making this water colder to touch. So you would see your thermometer go down. Okay, so we talked about that when we were talking about hot packs and cold packs last week. So this would be an endothermic reaction. Sometimes people get confused. They think, oh, that would feel hot, but it's not because the chemicals are absorbing that heat, and that heat is being used to do the reaction. So endothermic reactions, they feel cool to you. Okay, so heat was absorbed. You don't feel that heat absorbed. That heat is going into the chemicals to do the reaction. Alrighty. So let's flip. We're going to try one problem right here. And then you've got a very similar one down here to do. And make sure you are actually working these problems at home. I'm going to open up a discussion forum so you can compare your answers with other students in the class as well. That's going to be super important that you continue to practice and ask questions, just like you do in office hours. You can ask them in our discussion thread I'm going to open up on Canvas too. So just like we did in our earlier problems, we need to organize our information. So it says when 21.45 grams of potassium nitrate was dissolved in water in a calorimeter, the temperature fell from 25 to 14.14 degrees Celsius. They said, what is the enthalpy? So we want kilojoules over moles for the solution process. That's an important word right here. Process. This is, a process is, the act of completing something. We are dissolving water in a calorimeter. That is our process. Okay? Now you should have 2 columns of information, okay? Because we're talking about 2 different types of things. So let's organize our information. We were given our mass of potassium nitrate that we used, 21.45 grams. Okay, and they said that was dissolved in water. It made a solution, okay? So it says, what's the enthalpy for the solution process? The heat capacity of the calorimeter is 682 joules over degrees Celsius. So they gave us a bunch of information about the calorimeter. They gave us the heat capacity of the calorimeter. So that's big C. Notice the units. Just energy over change in temperature. And we also have the temperature change of the solution and the calorimeter. It started out as 25 degrees Celsius, and then it ended up at 14.14 degrees Celsius. Okay? So we've got all of our information organized. And what are we solving for? The enthalpy of the solution process. That is the act of dissolving the potassium nitrate. So this is what we're trying to find over here. Our kilojoules over our moles. Okay. Now we don't have anything about kilojoules, our heat, over here. We do have almost our moles. We have our grams. So can anyone tell me how to go from grams to moles again? We're gonna need the molar mass of potassium nitrate, simply the potassium nitrate. So if you add that up, it's about 101.1. So again, adding up 1 K, 1 N, and 3 oxygens from the periodic table. So we have 101.1 grams per 1 mole of potassium nitrate. Okay, you're not adding that with water. You can't combine 2 different chemicals there. We are simply dissolving potassium nitrate. Okay, we're not dissolving anything else. So when we divide that, we're getting 0.2122 moles. So we have our moles of potassium nitrate. So we've got that done. Now we need to find our heat. Well, we don't have any other information over here, but we've got a lot of information over here. We've got a change in temperature, and we have our our heat capacity of the calorimeter, our big C. So we can find the Q of the solution. I'm labeling this. This is of the solution in the calorimeter. So that's big C delta T. So we can fill that in. Okay. And then our change in temperature, always final minus initial. Okay, so notice we're going to end up with a negative change in temperature. So our Q of our solution, if we multiply this out, Our Q of our solution is equal to negative, circle that negative, 7,406. And our units are joules. So we have our joules. This is our Q of our solution when we multiplied this out right here. So if our solution is releasing heat, that means that when our potassium nitrate is dissolving, it is absorbing that heat. So really important, we need to make sure we switch signs when we transfer columns. Remember, heat lost equals heat gained. Heat released equals heat absorbed. So our Q for our potassium nitrate dissolving, the solution process, is equal to a positive 7,406 joules. Okay, so we've got that all done there. All right, guys, so we're almost done. We want kilojoules over our moles. We have our